Okay, so we're coming back together. Let me do a real quick introduction for Doug Cramer. He's one of our senior meteorologists. I think it's pretty safe to say that Doug has probably looked at more tornadic thunderstorms that have moved through the Ozarks, going back when you arrived, what, 97, 98? 2002. 2002. Ultimately, I put a lot of faith in what Doug tells me as far as radar signatures, and he's taught this class several times. We've always gotten pretty good reviews from people. I will tell you this, he's going to raise the bar as far as your understanding of radar. I don't have a lot of technical information, but stuff that I'm sure that you can put into play, whether it be looking at a GR or any other radar displays. So with that said, Doug Cramer.
Hey Steve, do you have is the remote working? You have this plugged in? By chance?
Yeah.
That just flip?
Should be good. It's back here. It's on this side.
Oh, is it over here? Okay. All right. Well, hey, thanks for having me today. I appreciate it. Looks like we've got a good crowd here. Don't think that's working. Real quick, I've been here since about 2002. For Steve, it may seem a little bit longer.
Sorry. We are taking this, so
Got a microphone. All right. Yeah, I've been here since about 2002. You know, I'm kind of a local kid. I grew up on a farm in southeast Kansas, just about an hour and a half west of here. And so went to KU, graduated from there, and then went to Jackson, Mississippi. When I started out at the National Weather Service, they call it Action Jackson down there, and that's kind of where I got my passions for severe weather, because I was supposed to make about $19,000 first starting out with the Weather Service, and I ended up making close to $40,000 with all the overtime that we had down there from the tornado outbreaks and stuff like that. So I brought that skill set up here to Springfield, and I just absolutely love this area. I don't know if I could ever see myself leaving the Ozarks. But we've had, quite a bit of weather since 2002, and we kind of realized that we needed a radar class for our partners, because now you have access to radar almost all the time. With smartphones, you can have radar with you just about anywhere you're at, as long as you got a signal. When we were teaching this class about 8 years ago, we used to tell you, you got to have a laptop and then all this stuff, and it was a lot more difficult to have radar data when you're out spotting and looking at thunderstorms, but it's pretty easy now. So if you're a spotter or a chaser, it's pretty important to understand radar fundamentals, and that's kind of what this class is about. I always try to make this as informal as possible, so if you have discussion topics, if you need to interrupt me with questions or whatever, feel free to do so, because the most important thing is you guys are absorbing the information and you're learning something today. But we've got quite a few radars across the area in the state of Missouri. We've got 3 of them, National Weather Service radars, Kansas City, St. Louis, and then right here in Springfield. I will say that as far as upper level observations go, when we release the balloon and that information gets into the model data, we're the only site here in the state of Missouri that actually does that. And it's nice to have, because we can sample those severe weather environments in real time before those thunderstorms get in, and it gives us a good idea about what's happening. But that's our radar network. We've got one to the southwest in Tulsa. It's actually just east of Tulsa, the location of that. We use the Fort Smith radar at Little Rock, and then sometimes in Oregon County, in the southeastern part of our CWA, we'll be using Memphis's radar, because they see a little bit lower than what we do. That's what the radar looks like. Most of you probably been out to the new terminal building at the airport. It's not so new anymore, but you'll drive right by that feature. It looks like a golf ball up on a big tower there. And the main 2 fundamentals that I kind of want to talk about today is going to be reflectivity and then velocity. We've got a lot of different products that we can use with the radar, including some dual pol data, which has been really good for us in being able to see tornadoes. But most of the time, I'm using these 2 things to diagnose whether storms are severe and trying to diagnose what kind of hazards are going to come from them still even today. You use the fundamental information that the radar gives you, and it's still, even today with all the fancy products out there, it still gives you the best indication on what a thunderstorm is going to do. And kind of the way the radar works, you know, it sends a pulse. You get a thunderstorm or some rain like today, even the drizzle, we're picking up on some of the drizzle that's out there. And it sends a pulse of energy out into the sky and basically circles the sky with those different pulses of energy. It travels in a sine wave. And part of that energy is reflected back to the radar. Not all of it, but part of it. So as you could imagine, the heavier the rain, the heavier the precipitation, the bigger the hail is, the more energy is going to be reflected back to the radar, and the radar can measure that amount of energy that's given to us. So that's how we know if we've got heavy rain or light rain or drizzle like today. So that would be reflectivity. And the velocity, we use basically the Doppler principle in understanding how precipitation particles are moving, and that allows us to see different circulations within thunderstorms. Now, this is the part that most folks really don't understand unless you've gone through an in-depth radar class, but we can see thunderstorms in a three-dimensional manner. So we're just not, you know, when you're looking at TV and they're showing you radar, they're just showing you a two-dimensional slice of what a thunderstorm looks at. But it's important for us at the National Weather Service, if we're going to diagnose how intense a thunderstorm is, we've got to look not only at the bottom levels, but the mid levels and then the top levels as well. So we're looking at a thunderstorm three-dimensionally. And the way the radar does that is that it tilts all the way up to 19.5 degrees when it sends out its pulse of energy. So it's going to send out a pulse of energy. It's going to sweep the sky at 0.5 degrees. Then it's going to raise itself, do the same thing at 1.5 degrees. And it continues that cycle all the way up to 19.5 degrees. And again, that allows us to understand the three-dimensional aspect of a thunderstorm. So if we have a thunderstorm that's developed about 70 miles east of the radar, so that would put it somewhere maybe in Wright County, and that thunderstorm is approximately 60,000 feet high. And the way the radar will scan that thunderstorm is you know, it basically looks at every single level of that thunderstorm. And when you have a hail core that develops, say, somewhere between 30 and 50,000 feet, we're able to detect that hail and view how intense that hail is by looking at the 3.5 degree slice. So that pulse of energy that's traveling at 3.5 degrees, we're seeing the bottom part of that hail core. And then we're also seeing it with the 4.5 degree slice. We're looking at the middle and maybe the top of that hail core, and the very top of that hail core at 5.3. So when we talk about, when we're on NWS chat and we're saying, yeah, I've got a core, the top of that core is about 25,000 feet up. That's kind of what that means. So we're really diagnosing the strength of the core of the thunderstorm to give us an idea about how intense the thunderstorm is. If the core isn't really exceeding about minus 15 or minus 20 degrees up above the atmosphere, then it's going to have a difficult time generating hail that's going to sustain the warm layer and reach the ground. So we're really looking at these cores above about 20,000 feet. And so if we're saying, yeah, we've got a core top that's up to about 35,000 feet, it's really intense, then the probability of large hail reaching the ground is really going to increase at that point. So here's an example. This was the Stockton supercell. This is still the best thunderstorm I've ever worked. You know, I issued the tornado warnings for every single county across our CWA, from Wichita's area up to St. Louis, and verified every single county with this thunderstorm. So it was I may never get to work another thunderstorm like this, but this is when it was hitting Stockton, May 4th of 2003. With a EF3 tornado, and previous to this in southeast Kansas, it wiped out a town called Franklin, Kansas, there in Crawford County. That was really close to being an F5, but we called it an F4. But it did carry a vehicle about a mile from where it was located at, so that just gives you an idea about how intense that storm was. But this is an example of how we three-dimensionally look at a thunderstorm. This is looking at the half-degree slice. You can see a really nice hook echo on this. The tip of that hook echo, which is the tornadic location, is right over the middle of Stockton there. And so we're looking at that thunderstorm at about 3,000 feet up. If we raise that radar tilt up to about 1.5 degrees, now we're looking at the storm at about 6,500 feet up. And some of you guys have real good in-depth knowledge, like Brian DePriest over there and Richard Vaught. What do you notice about that slice? Professional storm chasers over there. Yeah, well, no, it's not a hook anymore. It's actually what we call a bounded weak echo region. So the hook is wrapped around all the way back into the forward flank of the storm, and we have a weak echo region right here, a little donut hole. That's what we call a beware. We're going to talk a little bit more about bewares later, but when we see a beware like that, we know that updraft is especially strong there. So when we look at that, that's kind of a red flag to us that we're dealing with an unusually intense thunderstorm. So when we raise the radar slice up to 2.5 degrees, then we're looking at the storm here at about 10,000 feet. And then you notice, well, we don't really have much of a hook echo anywhere more or a beware. But we do still have a weak echo region here on the south part of the storm. And that's still indicative of a very intense updraft. And then when we raise it up to 3.5 degrees, we're looking at about 14,000 feet. And then when we look at 4.5 degrees, that's kind of what that storm looks like. You're just kind of starting to sample maybe the lower part of the hail core. And so a warning temp for us is hail equal to or greater than 3/4 of an inch, of about the size of a penny, will usually occur when 55 dBz or greater reflectivity exceeds that -20 level. So now we're starting to exceed that -20 level. From a temperature standpoint, that -20 level was sitting at around 19,000 feet, but now we're looking at this storm at about 21,000 feet. So basically all of this red shaded area is indicative of hail that will likely reach the ground. So that's a pretty large hail swath there that covers about 1/3 of Cedar County. And that's looking at about 5.5 degrees slice. Now we're looking at about 24,000 feet up. We still got a lot of red shaded area there, indicative of hail. So a very strong updraft, looking at 30,000 feet at the 8.7 degree slice. We also look at these types of thunderstorms looking at vertical cross sections. So we could basically utilize our radar and we could draw a line through a thunderstorm and it gives us a vertical cross section. So we're not looking at a two-dimensional plane anymore. We're looking at a specific area from the ground all the way up to about 60,000 feet with this thunderstorm. The top of the core is reaching at about 42,000 feet. So if our -20 layer is about 19,000 feet and above, we could easily draw up a cross section and see all of this massive area right here in this thunderstorm would be indicative of hail up to the size of 3/4 inch or maybe even larger. In this case, it was baseballs. So this is a pretty easy warning decision for us at the National Weather Service to at least get a severe thunderstorm warning out. And then if the rotation is dropped all the way down to our lowest slice and is tight enough, we may have to get a tornado warning out on it as well. Sometimes we look at these thunderstorms in different panels. We can look at thunderstorms. I actually have a 12 panel. This is what we call a 4 panel, where I'm looking at different elevation cuts of the same thunderstorm at the same time. But our computer systems are quite a bit more robust now, and we can look at 12 different cuts and elevation angles of a thunderstorm, and that's one of the procedures that our meteorologists tend to look at. And it just helps us not only with a two-dimensional perspective, but a three-dimensional perspective of the structure of that thunderstorm at the same time. So it's pretty cool, and if you ever tour the office, I'll show you that. It's pretty neat to be able to look at storms like that. Severe weather signatures, talk a little mostly about supercells because that's Steve Runnels' favorite type of storm. He doesn't like squall lines much, but we'll talk about the big boys here. And we got the hook echo. Most of you that's had spotter training, we know that that's a red flag signature there, where we don't even have to look at velocity to understand that storm's rotating because it takes counterclockwise rotation to be able to form that hook. And then your tornado location is going to be right there at the tip of the hook. You got the hail, the heavy precipitation area here in the forward flank. Sometimes if you got some really strong jet dynamics above the storm, that's helping it from a vacuum standpoint, and it's helping that updraft becomes a little bit more enhanced and stronger in nature. Then you'll have what we call a V-notch right here, so that you got the thunderstorm poking into those jet dynamics, and it's creating a divergence signature up here in the radar information. This was March 12th of 2006 in Webster County, southeast of Marshfield, right around I think they call it High Prairie. Yeah, High Prairie area there. And we had a F3 tornado that went through there. There was a guy that was hit by that tornado and carried a certain distance with the tornado, and he survived, and it made like the Guinness Book of World Records of a human being carried by a tornado and surviving. And he ended up on David Letterman, believe it or not. And just north of Portland there, High Prairie. And so, this is a typical tornado signature here. This is our rotation. So the black hole here is our radar. And we're looking in east central Webster County. You can see these really bright pinks. That's indicative of winds that are going away from the radar, right next to these bright blues, sky blue color. That indicates very strong winds going towards the radar, and they're right next to each other. So it's gate-to-gate circulation. It's real tight. It's real strong. And you notice that it's basically right underneath the hook of that storm. So you see where the hook echo is, and there's where your tight rotation is. And that's where your tornado location with a classic thunderstorm is going to be almost every single time. So if you're spotting, you don't want to be in this part of the county. You don't want to be behind it because you're not going to see it over there in Marshfield. Fordland, if you're just northeast of Fordland, you might be able to see it, but you're still going to be having an obstructed view. If you're in Seymour, you might be able to see it, but the best location, if this storm's moving east-northeast like it was, would be just to the southeast of it. So that's kind of where you want to be, but then you have to think, well, if the storm begins to peel to the southeast, then you're going to be right in the path. And that can get people in trouble. It's gotten me in trouble before with the Pitcher tornado, where I had a close call with that. So here in May 4th, 2003, we've got 3 different supercells here. That was in southwest Missouri. This was the Stockton-Franklin storm. This ended up being the Carl Junction storm. And then this ended up being the Pierce City to Battlefield storm. And then you can see the 3 different velocity couplets here with these thunderstorms. All of them showing very strong rotation in the low levels. Sometimes these storms, we had one the other night. We were working where it showed some pretty strong rotation at about 15,000 feet up. And that doesn't necessarily mean we're going to issue a tornado warning on it. We got to be able to see that rotation actually fall a little bit closer to the ground before we have a little bit more confidence in issuing a tornado warning. So in NWS chat, when we're talking about these types of signatures, we may say, hey, we got rotation really high aloft. It's elevated rotation. Severe thunderstorm warning will continue. Or we may say something to the effect, storm moving into Lawrence County. The circulation has dropped now to about 3,000 feet. Now we are considering a tornado warning at this point. So that's the kind of communication that NWS chat gives you guys, that gives you some confidence in knowing what you need to do and what our perspective is on a storm. Talked about the weak echo regions. This is a particular thunderstorm that impacted Ted Martin there in Branson. How deep was that hail that night there, Ted? March 12th, 2006. You remember how deep that was? I saw pictures of hail that was like right around this deep, and that was from this storm here. And it was coming out of Arkansas. We thought for sure this was going to be the Branson tornado, but it decided to hold off another 6 years. But the thunderstorm, very strong updraft here, what we call a weak echo region, a little bit of a hook appendage there in the low levels that was coming out of Rogers, Arkansas. And then once we get up to the 1.5 degree slice, you can see the donut hole right there. That's the bounded weak echo region signature again. And we knew that storm was especially strong when we're seeing signatures like this with the weak echo right in the middle of that storm, indicative of a very powerful updraft that's not allowing the radar to see any of the precipitation particles that's there, or a very weak part of it. And that's at about 13,000 feet. This is at 20,000 feet. Don't really see much of a signature there other than the hail core, and then you can see a pretty good hail core there at about 3.4 degree slice. So that would be a weak echo region here on this quadrant. This is a bounded weak echo region, hail core aloft and the hail core aloft. And then later on, as the storm moved into southeast Stone County, so it's pretty much over Table Rock at this point, you can see that, again, we got the weak echo region, bounded weak echo region here, and then it becomes a complete donut hole right here in southeast Stone County, and then the bounded weak echo region here. We thought for sure Branson was in big trouble when the storm was coming in from the southwest. I think maybe we did have a weak tornado somewhere with that, but the big impact was all the hail that Branson got that night. One of the ways that we can see hail, another really good way that we can see hail is by looking at what we call a hail spike, and you can see a little bit of weak reflectivity that's spiking out of the center of the storm. So it's called a hail spike. If you're a meteorology professor, you better call it a three-body scattered spike, but typically in NWS chat, we try to simplify it, and we'll just call it a hail spike for you. And the reason why that happens is if you get hail that's falling out of a thunderstorm, that pulse of energy hits that hail, and then some of that energy is reflected to the ground, and then it hits the ground, it's reflected back up into the hail, and then it reflects off the hail and back to the radar. So it was reflected 3 different times. That's why the professors of the meteorology community call it a three-body scatter spike. But again, we'll just call it a hail spike just for simplicity's sake. The storm that I was just talking about that was coming into Branson that night, you can see a big-time three-body scatter spike or hail spike coming out of that right there in northwest Arkansas. And that, I don't remember what slice that was or how high we're looking at, but that was kind of the meat of the middle part of that hail core there with that storm. And we'll talk about these things a lot in NWS chat when we're trying to describe these storms for you. So again, you can see the different three-body scatter spikes. This is looking at the lowest tilt, but if we look at the 1.5, the 2.5, and 3.5 degree slices, you can see a hail spike in a very deep level of that storm. So not only are you seeing weak echo regions, but you can see a hail spike that extends, the depth of it was thousands of feet there. So that's part of the reason why Branson got all that hail that night. The debris blobs, we can see debris blobs, but since we've gotten dual polarization, which I'm going to show you a little bit in this presentation here today, we can actually see tornadoes. We used to tell you that we can't see tornadoes, but in February of 2012, we were able to install new technology. It's called dual polarization, and because of that new technology, we can actually see debris in the air. And about 2 weeks after we installed it, we had the leap day outbreak when Branson really did get hit, and along with some other communities, and we saw for the first time in our careers tornadoes with the radar. So the radar, with how old the radar is, it just amazes me how we continuously get more and more out of it, and we continuously increase the technology, and it's just going to continue to save lives. But this feature here at the tip of the hook, we always talk about tornado kind of being at the tip of the hook. That's the most dangerous part of a supercell. Sometimes we get an enhanced reflectivity there at the tip of the hook, and that's the radar sampling into 2x4s and sheet metal and stuff like that from a tornado. The Joplin tornado gave us a really deep debris blob that day. So velocity data, so this was the Webster County storm again. This is this is one of the best signatures that we can see with the radar that helps us. But there's different types of circulations. You don't always have to have a tornado circulation. there's different types of circulation that gives us clues about what a storm is doing. So this is what we call a pure rotation. So if the radar location, if we're looking at this image here, the radar location is down here. So the reds are winds going away from the radar, the blues are winds going towards the radar. This is pure rotation, and this is what your wind field would look like if you've got a pure rotation in your thunderstorm. So that's a pure rotation circulation. But here's what we call a divergence. This is not pure rotation. So your radar location is down here, this yellow circle. Your blues, again, indicate winds that are going towards the radar. Your reds indicate winds that are going away from the radar. This would be a divergence pattern. And can somebody tell me, when will we see a divergence pattern? Yeah, downburst. So it's basically, it kind of has to be a little bit closer to the radar, because we got to be able to see the, if you're shooting up too high, you're not going to be able to see a downburst. But it's essentially a microburst that crashes to the ground, and then it spreads out. And when we see that, if we don't have the warning out, we already missed it. So there's no point in getting a warning out. You just missed a microburst. And we typically see these a lot, like in July and August during our pulse thunderstorms, when microburst frequency starts to increase with those types of thunderstorms. Convergent rotation. This is something that we'll talk about on NWS chat when we see it. So again, your radar location is down here below the picture. You've got winds going towards the radar with the blues, winds going away from the radar with the reds. It's not pure rotation, right? Because it's not side by side. It's kind of converging on itself. And this is a signature that can occur right before tornado formation. There's a lot of research that shows that right before the tornado forms, you have more of a convergent pattern. You want to see that convergent pattern more so than an actual pure rotation pattern. So this is right before a tornado forms. This is a big-time red flag, even more so than pure rotation for us. And that gives us a little bit more confidence that a tornado is going to form. So you got rotation, but it's all converging in on the center of where that tornado is getting ready to form. Just because you got convergent rotation doesn't mean you're going to always get a tornado form, but it's the research shows that this typically happens right before tornado formation. And then we have a divergent rotation. So again, radar's down here. Blues indicate winds going towards the radar. The reds indicate winds that are going away from the radar, but it's kind of diverging while it's rotating. So the wind field looks like this. It's going away from the center, but it's rotating at the same time. Anybody can guess, can you guys guess what that typically means? Because we see this too. Do you know what divergent rotation means? That means that the tornado has either dissipated in a supercell or it's getting ready to dissipate. If I see this and I've got a tornado warning out, that next county downstream, I may not put a tornado warning out, because this is a pretty good pattern here that tells me that that storm's becoming less organized and the tornado's getting ready to dissipate, or maybe it has dissipated. And again, this is something we'll talk about in NWS chat. We'll say, yeah, I got a divergent pattern. Central Christian County, probably not going to warn on Douglas County at this time unless it begins to become a little bit more convergent or pure and a little bit more organized in nature. So chances of tornado development significantly increases if you get convergent rotation. And this was the Stockton supercell, so May 4th, 2003, Stockton supercell. This lower slice up there, this is a half-degree slice. We're looking at about 3,500 feet. What kind of rotation would that be? So the radar's about over here in the corner. It's off the picture. Yeah, so that would be convergent rotation. That is a bad sign. And that day it was a bad sign for the city of Stockton there. Tornado was actually already on the ground when we saw that. So we look higher aloft. What kind of rotation is that at about 7,000 feet there? What would you say that is? What's the structure of that rotation? So that's probably a little bit more pure, right? So if you get the convergent rotation down low, that doesn't necessarily mean you're going to have that same rotation above it. The convergent rotation down low is bad. I can tell you that. So other areas of the thunderstorm, 12,000 feet, it's more of a pure rotation. And then 17,000 feet, that's also more of a pure rotation. And then one other point I want to make of this image here is that when we make tornado warning decisions, the deeper the rotation is, so this rotation is basically almost all the way to the ground, 3,000 feet to 17,000 feet. That's a very deep level of rotation, right? So if we've got time, continuity, and then depth of the rotation, then those are two signals for us that increases our confidence for issuing a tornado warning. So that's a couple of good topics there to remember when you're analyzing radar data. Pulse thunderstorms, July and August, we get them. They don't get them much in Kansas, but we're kind of on the western fringe of geographically where we can get the summertime tropical air into southern Missouri. There's not a whole lot of wind, not a whole lot of wind shear that's going to organize these types of thunderstorms. They just kind of pop up at random. If you're used to canoeing on rivers or being out on the lake with your boat and stuff like that, you have to watch out for these. I've gotten caught 2 or 3 times with these types of thunderstorms. They just kind of pop up out of nowhere, and then you're dealing with lightning. They can also give you microbursts. So again, it's that air updraft goes up, there's no wind shear to organize it, and it just collapses on itself. And that can give you, some good 70, 80, 90 mile per hour winds sometimes into those microbursts, and they can be quite damaging. Not all of them are going to give you microbursts, though. And it's very challenging for us because sometimes from a radar standpoint, every single one of these little thunderstorms can look almost identical, and only a handful of them give you microbursts, and then the other ones really don't do much at all. So it's difficult for us to discern, okay, which ones do I need to warn for? And it's a lot of difficulty to it. And that's where spotters can sometimes help us. This is a typical signature here. So the radar's this black hole. You've got a low-level divergent signature because the greens indicate winds going strongly to the radar, and it's right next to some winds that are going away from the radar. So this is a divergence pattern right here. What just happened? Yeah, not a tornado, but a downburst, a microburst. Yeah, and sure enough, we had a farm that was hit right there on the Polk, Dallas County line. Had some damage with that microburst there. This is one that I was working one day. I missed it. It was a pulse thunderstorm just south of Ash Grove, close to Halltown. And all of a sudden, this signature popped up, and I was like, just missed it. And sure enough, we had a bunch of trees. There's a farm down there, and there's a bunch of trees down with that microburst there and that divergent signature. So wind's going towards this black hole, wind's going away from it. Beautiful microburst signature there. And we'll talk about this stuff. I talked with Patty many times. I remember, these summers that we've had in the past where, I'm telling her, okay, we're very confident in a microburst happening right here near Fremont Hills, or, we're by just Rogersville. We got a divergence pattern here, microburst signature here, and then she'll start making her calls and stuff like that and getting us the reports and stuff like that. So these are good confirmation signals here. There's another one up in Polk County. Radar's here. Green indicates winds going towards the radar. Red indicates winds going away from the radar. And now, here's another pulse thunderstorm. Radar's here. And so we're 2 counties to the east, which would be Wright County. I'm very interested in this storm here. I'm looking into this storm at about 12,000 feet, so it's a little higher up. And what kind of rotation or circulation do I have? So I got the greens going towards the radar. I got the reds going away from the radar. That is not divergence. That would be a pure convergence signature. So I'm looking at 12,000 feet up. It's a pulse thunderstorm. I've got a pure convergence signature. This is what we call a mark, a mid-altitude radial convergence signature. In NWS chat, we'll typically call it a mark. And that's indicative. That is one of the precursors, one of the few precursors that a pulse thunderstorm will give us that's getting ready to tell us that a microburst is about to happen. So what's going on there? 12,000 feet up, the microburst, that air is starting to collapse, And when it collapses through that column, the air has to fill in behind it. And that's why the convergence is happening. So that gives us about 5 or 10 minutes of lead time to get a warning out for you guys that a microburst is about to happen. So when we get that pure convergence signature at around 10 to 14, 15,000 feet up is what we're looking at. Mid-altitude radial convergence signature. Beautiful signature. Okay, and then we're about done with our signatures here. So we've talked a lot about the low levels. We've talked about the mid-levels. Now we're looking at the very high parts of a thunderstorm. And there are signals and clues in the high parts of a thunderstorm that also tells us what it's getting ready to do and how strong it is. So this is a reflectivity image of a supercell at about 40,000 feet up. So it's moving out of Ottawa County, Oklahoma, moving into Newton County, Missouri. 40,000 feet up, see a little bit of red there, so most likely that storm's going to have some hail. The core, top of that core is up there quite a bit. All right, now we're looking at the velocity of this thunderstorm at 40,000 feet up, and I'm particularly interested in this area here. The radar is over here in Springfield, off the map there. And I've got these bright sky blues moving towards the radar, and then I've got these yellows and reds indicating the wind's going very strong away from the radar. And that is what we call storm top divergence. And the stronger a thunderstorm is, the more intense a thunderstorm is, the higher that storm top divergence is going to be. So it's almost like an upper level vacuum that's acting to enhance that updraft. And the stronger your updraft, then the more intense your storm is going to be. So we're looking at about our threshold, according to some researchers that studied the storm top divergence. Once we get about 75 knots or more storm top divergence, then chances are that storm is going to become so intense that it's going to be severe. So we'll talk about storm top divergence quite a bit. Bow echo signatures, man, we've come a long way with squall line research. And we know a lot more about squall lines than what we did about 10 years ago. This is one that occurred on the morning of July 4th, 2004, and it produced it's almost like a derecho type event there across southern Missouri. It produced a tornado. We know that squall lines produce a lot of tornadoes, probably more tornadoes than what supercells do in Missouri. And when we've got families of tornadoes and TDSs that are popping up with these squall lines, that's pretty much 100% verification that these things are producing more tornadoes than what we realized in the past. They're typically not going to be your F5s or anything like that, but they are tornadoes and they still do damage. The bow echo evolution, these things typically start out as a cluster of thunderstorms and they tend to elongate, and then you start to see some bowing. And then that's kind of the mature stage of the bow echo. And then right at the apex of this bow is where you're going to get your damaging winds and then your tornadoes as well. So locations in advance of the bow apex typically experiences the greatest wind velocities and then also tornado production. Ottawa County, Oklahoma, right here. We had a 6-year-old girl that was killed by a 100-mile-per-hour wind knocking over a tree into a mobile home. Produced a tornado right there in the town of Hornet. So it goes over Table Rock Lake. We had one injury there of a guy that was accidentally thrown into the lake with the high winds that came through. He was trying to tie up his boat. Ended up being okay. But this thunderstorm formed over Kansas, moved across northeast Oklahoma, southern Missouri, and it finally died in eastern Kentucky. So it was a long-lived line of thunderstorms on steroids, and that's typically what we call a derecho. So a derecho is going to have kind of a long lifetime and a series of damage patterns with it throughout its lifetime. The July 19th Table Rock Lake storm was also classified as a derecho that day. July 4th derecho, again, one tornado. We probably may have had more if we had dual polarization to show the TDSs with that storm. But the most significant winds were here. I was in Craig County, Oklahoma at my parents' house. and that was probably the strongest winds I've ever felt. And it just looked like a plasma looking out the window that morning when it came through there. All right, and then to wrap this up, this ground clutter stuff. Does everybody know what that is? It's just like it's the radar. That's very sensitive. It's at nighttime. The radar, because of the thermal dynamics in the lower troposphere and the inversion that sets up sometimes the beam will bend down to the ground and then reflect back to the radar, and it gives you like super high reflectivities. That's part of this, what we call ground clutter or anomalous propagation. Bugs, airplanes, sometimes we see 18-wheelers on Interstate 44, and we can clock them with our radar, believe it or not. I think this is Ron Hurst's favorite term, anomalous propagation. He uses that a lot. Sometimes you could get, it creates a messy situation, and it can be kind of confusing if you're not used to looking at radar, especially when you have anomalous propagation or ground clutter mixed in with real precipitation. So this would be like a real thunderstorm. This is not real. And if you're not sure if it's real, what you can do is animate your radar, and if it's moving, then you know it's real. And then finally, tornado debris signatures. This is very important. This was the Table Rock Lake to Branson tornado on Leap Day. This is one of the very first tornado debris signatures that we saw. It was a squall line system that came out of northwest Arkansas. Here in the reflectivity, the one thing that I noticed, and I warned on the storm, it was moving 75 miles per hour. A lot of people don't think that you can get tornadoes, especially strong tornadoes, when a storm's moving 75, 80 mile per hour, but you can. And this one was moving 75 mile per hour. We gave Branson really good lead time. We didn't give Tom Martin lead time over in Stone County very much, but we gave Ted Martin really good lead time with this storm, about 20 to 25 minutes before it got into with the tornado warning. You can also, one thing that we typically find with squall line tornadoes is a front inflow notch coupled with a rear inflow notch. That's what we call a coupled inflow notch with squall lines. When I see that signature, it's a red flag that we see a lot of squall line tornadoes with that type of signature. You also here got a velocity couplet in our velocity. And then at night, this is one of the very first the tornado debris signatures that we saw. This is very messy data, but you can see a blue donut hole right here where our velocity couplet is, and then right there in the middle of our coupled inflow notch with the reflectivity. And you can see, I really want you to focus on these two donut holes there, because that's the radar sampling into the 2x4s and the shingles and all the stuff that the tornado hit over there by Kimberling City, the boat docks, the houses and stuff like that. And that's the radar sampling into those features there. So the radar is basically saying this isn't normal precipitation. This is something else. And so we can follow that. It even gets better once it crossed Highway Double D and then Indian Point. The more houses and trees that it hit and structures that it hit, the tornado debris signature became even more defined that night. And then right at this point, I was working radar. I saw it basically right over the crosshairs of Branson. I was like, ugh, this is not good. And then you can follow it east of Branson over towards Power Site, and then we lost it right about there. We weren't really sure where the end of that tornado was, and we had a pilot, one of our pilots that's really interested in looking at tornado damage over in Berry County. He's a retired United Airlines pilot. He actually flew that for us and got us an endpoint, and it was just in the woods out there somewhere in eastern Taney County, east of Power Site. Buffalo, this one even showed up even more. This was the same night. So this is another QLCS tornado. It was another EF2 tornado. And you can see as it crossed the Polk and Dallas County line, I really want you to focus on these two images here down below. You see nothing there, and then boom, all of a sudden this blue donut hole pops up right here. And that was the tornado hitting a turkey barn. I think, Steve, you may have surveyed that one, or maybe built it. I can't remember. But it hit a bunch of turkey barns right there. So it was sampling into like sheet metal, and sheet metal is highly reflective. to a radar. So this was a beautiful, beautiful TDS. Also hit a mobile home park on the south side of Buffalo there, and then you can see how the TDS is small, but then it gets bigger, and that's not necessarily the tornado getting bigger. It could be getting bigger, but it's the debris field. So it's debris that's shooting out of the tornado, and it's making the TDS look a little bit bigger as it moves out of the area there. Now, this is the Hoiberg tornado in Lawrence County. This was January 21st of 2018. Very tiny. This is what we call it. This thing didn't even have lightning, but it was structured like a supercell, so we called it a super shower. And so you got this. It's got like supercell structure. It's got rotation here. And then all of a sudden, boom, this little tiny TDS popped up right there. And this is the beauty of TDSs, because that night, what we were able to do on NWS Chat, Missouri Highway Patrol Troop D was monitoring. We were able to tell them the exact location of where the TDS popped up. They went to that location and they found the damage, and they were able to go in there very quickly to make sure everybody was safe and okay. So these are, we try in NW's Chat, that's one of the concepts I want to make sure that you guys understand, is when we see these things and we're confident in them, we'll tell you. And that way emergency services personnel can go to that location and make sure that people are safe. All right, is my time up? Okay, we'll do a few exercises here. The image below, this will be real quick, guys. The image below is just a little test for you. Is an example of what type of non-precipitation radar phenomena? Yeah, so ground clutter, right? And what's Ron Hurst call it? Anomalous propagation, yeah. And then which area, A or B, on the image below represents actual precipitation? Yeah, so it'd be. And then what's a way to know for sure? Yeah, animate it. And whatever's moving is precipitation, and then whatever appears to be kind of sitting still would be your ground clutter. What type of circulation within the yellow circle does the radar indicate? So just to kind of help you, this black circle here is the radar. That's a cone of silence. So I'm hearing convergence, I'm hearing divergence, and keep in mind this is low, so about 1,200 feet up. So the greens indicate winds that are going towards the radar. Reds indicates winds that are going away from the radar, so that'd be a low-level divergence. And again, that's indicative of a microburst that just happened. Identify an area on this half-degree reflectivity image most likely to receive damaging straight-line winds within the next few minutes. It's about right there. Yeah, and then notice the fine line right here. So that's your outflow, and that's what we're going to be warning on. I was the warning operator of the day of the July 19th incident at Table Rock Lake, and I was warning that day, and thank God I was, but I was lining up my warnings with this outflow boundary, and that was a day where it was pushed out ahead of the convection, because that's where the impact is. That's where you're going to see the winds first. It's not going to be with the red. It's going to be with that fine line. And we learned from the Indiana State Fair with the stage collapse that that's what you got to do from a timing standpoint to allow people to understand when it's going to get to a certain location. On the images below indicate the location of the hook echo, a possible tornado indicator. And where would you place a trained spotter to best monitor the tornado potential if it's moving to the east-northeast? Yeah, so you'd place a spot around Hoover, maybe, what's that, Hueytown? And then your hook echo's right about here. And then your tornado location within the hook is going to be where? Yeah, typically right there at the tip. So it's a big storm. It covers a big county area, and it's important for a spotter to understand where the tornado is going to be. It's not going to be up here. It's not going to be over here. It's going to be right there at the tip of the hook. And that's where you want to be placed, right about there. What type of circulation within the yellow circle does the radar indicate? You're looking at about 12,000 feet up. Yeah, mid-level convergence. And so we typically call that a MARC, mid-altitude radial convergence signature. And what's getting ready to happen? Yeah, microburst. It's another microburst signature. It's interesting. Microburst signatures can be divergent and convergent, just depending on what part of the three-dimensional aspect of the storm you're looking at. That's why it's important to look at storms three-dimensionally. And then locate the three-body scatter spikes in the two images. Can you see the hail spikes there? Yeah. So you can, couple obvious hail spikes there coming out of the storms. You see that on radar, your confidence in large hail increases within the next few minutes. And what type of circulation is this here within this yellow circle? Looking at 40,000 feet up, the radar is over here. Yeah, that's your storm top divergence. And the stronger that is, the more of a vacuum effect that you have on the top of the storm, and the stronger your updraft is going to be. So we look at that quite a bit. And then what type of signature is that? Donut hole. You guys want us to call that donut hole on NW's chat? Does that make it easier? The TV guys would be like, what the hell's a donut hole? Yeah, so that's a bounded weak echo region, right? Bounded weak echo region on that one right there. So, and that means very, very strong updraft in that storm. So it's a red flag for us. And then this would be a weak echo region. So you also have the appendage, and then maybe you could call this a hook. But this concave weak echo region here is what we call a weak echo region. It's not quite bounded yet. It's not the donut hole yet. It may be getting ready to be, and it may be a loft. But at that level, it's not quite bounded yet. Clear air slot. Yeah, I haven't heard that one yet. What type of signature is the radar indicating down here? Yeah, so it's a tornado debris signature. It's a good signature. All right, I think this is, got two more here. Okay, thunderstorm forms. All right, it's real close to the radar. It's within about 25 miles. And you get this hail core that develops up here in the mid and upper levels of the storm. Are you going to be able to see that hail core if you're looking at your base reflectivity down here? So what slices are you going to have to analyze to be able to know the intensity of that storm? Yeah, so you're going to be looking at that 8, let's see, about 10 and above. So 10 to 19 and a half, you'll be able to see that hail. All right, but the storm moves now. It's over, let's say, Webster County. And the hail core, not only does the storm move, but the hail core drops. So now what slices are you going to have to look at? Yeah, so you're 1.5 to 4.5 to be able to see that hail. And then the storm moves even further. Let's say it's over Shannon County now, Jacks Fork River, and the hail core redevelops up high. Yeah, 1.5 to about 3.5 is where you're going to be able to see that hail. And that's how we have to analyze storms. Flooding, storms that are very rain efficient aren't typically very tall, and they usually happen in very warm environments. In this situation here, your heavy rain core is going to be here, kind of low at about 10 to 20,000 feet. If the storm, in this case, moves like over Shannon and Oregon counties, maybe over West Plains, then our lowest slice is going to be shooting over most of that heavy rain and our rainfall estimates from the radar may not be very accurate. So that's one thing to consider. The further away that we get from the radar, the less accurate our rainfall estimates are. Yes, sir. So basically, it's an updraft that's suspending that hail. So the updraft is strong enough to suspend that ice up there. And the longer it can become suspended, the more super cool water accumulates on it. And it gets bigger and bigger and bigger to where the updraft cannot sustain it anymore, and then it eventually falls. It's tremendous, yeah. Just to kind of give you an idea about how tremendous an updraft can be. So the Buffalo tornado, where I showed you guys the turkey barns that were hit, and we were showing you those TDSs. In a 4-minute time frame, that sheet metal went from the ground to 10,000 feet. That's how tremendous an updraft can be. And you don't have to have a tornado. A tornado is an updraft, so it accelerated that sheet metal. But, an updraft of a storm, it can be like 90, 100 mile per hour. So as you can imagine, if it's that strong, it's going to suspend that ice until it just gets so big that, gravity's going to win over at that point. And that's another thing to think about too, and pilots know this, is that super cool water is actually water that hasn't turned to ice but is below 32 degrees. So you're going to have that super cool water up there above the freezing level that helps that hail development become even more bigger. So, any other discussion topics, yes, sir? Yeah, European models is ran, I believe, is it in Germany? I think it's Germany. The GFS is produced in Washington, D.C., so that's kind of an American model. There's a lot of American models. Canadian model is produced in Toronto. So the environmental Canada is what they call that. And then you have the UK model, and that's produced in London. We have access to all of those models, and typically they'll show different things. So it's up to us as humans to try to predict, what model or maybe what combination of models do we want to use for our forecasts. And it seems like as time goes on, the more and more models that we have, there's a lot of American models, but those are what we call global models. And we also have more of a localized models like the NAM, and some of our CAMS outputs, or our the convective allowing models is what they call those, that tries to forecast what the radar is going to look like in time. Those aren't necessarily global models. Those would be more of American regional models. And just kind of depending on what we're striving to predict is what model we determine to use. And some of them we know that just aren't very accurate, in certain situations. In the wintertime, it's been my observation over the years, the European model, when trying to forecast winter weather, is typically a little bit better with its mass fields. Yes, sir.
I have one quick basic question that kind of illustrates why you need us as spotters, and the map here shows it best. You're shooting your lowest lights at a half degree up from the horizon. At 100 miles out, how far down is the ground from that half degree up?
Yeah, so if we're looking at that storm like over West Plains or Shannon County, which is still in our area, yeah, it's like 11,000, and like in Oregon County, it could quickly go to about 16,000 that we can't see under it. So does everybody want to move to West Plains and Oregon County and Shannon County? You guys want to move there to help us out with that? Yeah. So are you in Joplin? Yeah. Well, we got a little bit better. You're only 2 counties away. So we got a little bit better coverage over there. But once you get you also got Tulsa's radar. I don't think Joplin's necessarily, I don't really think I feel pretty comfortable with Joplin. Once you get over towards like Neosho County, Kansas, you start to run into a hole over there, like Chanute. Yeah, like Chanute, and maybe like Montgomery County, Labette County, Wilson County over there, because you're right there in between Kansas City, Tulsa, and Wichita. I think that's a little bit more of a hole than what you guys are. Now we consider like the eastern Ozarks from the Highway 19 corridor from like Alton, Thayer, all the way up to like Salem. That's a problem area for us. If we had to put a radar somewhere, it would not be Joplin. It would be West Plains. If we could get another radar. All right, thanks for having me, guys.
I for one, want to especially thank Doug. He came in, left his family behind. He drove all the way in from Stone County for this presentation. So I definitely appreciate it. But Doug, I do want to let you know, we were talking time earlier, and the fact that you beat the over-under. I had thought 90 seconds before you mentioned Kansas twice, and you got the time in there. I was very impressed. About as long as your team lasted in the tournament this year. Actually, it's the young lady in black that. There was the young lady in black there that was talking about Duke, so I had to throw that in there before she beat me to it. All right, guys. We've talked about storms from a spotter's perspective, from a radar perspective. Patty's going to turn it around now. She's going to talk about it from a net control, situational awareness perspective, utilizing a lot of our own material. So I'm looking forward to seeing what she has to say, because I haven't seen your presentation yet. And I look forward to hearing the pieces of information that you pull out of what we're sharing. With that said, the time is now 11:48. This is important. In order to get you out on time, we'd like to take a quick 5-minute break. Okay? 5 minutes. Thank you.
Not at the moment, no.